This presentation introduces Nova LSM, a distributed component-based implementation of an LSM tree key-value store. I conducted this research with my advisor, Shahram Ganharzadeh, in the database lab at the University of Southern California. Nova LSM is based on log-structured merge tree, LSM tree. LSM tree is introduced in 1996 and implemented in many modern database storage engines. LSM tree optimizes write performance. Google open sourced an implementation of LSM tree called LevelDB. Facebook's RocksDB extends LevelDB with more features such as richer schemas and transactions. There are also many distributed data stores that store data using LSM tree. Examples are CockroachDB, Cassandra, Siler, and AsteriskDB. LSM tree is suitable for write-heavy workload. I will briefly describe Google's implementation of LSM tree, LevelDB. LevelDB buffers writes in the in-memory mem tables and flushes them to disk as sorted string tables, SS tables, when the mem tables become full. Keys are sorted inside the mem table and the SS table. LevelDB organizes SS tables on multiple levels. Level 0 is summary sorted, while the other levels are sorted. Each level has a size limit to bound the storage size. When the size of a level exceeds the limit, the compaction merges its SS tables with the overlapping SS tables at the next level. It writes the new SS tables into the next level. In this figure, a compaction may compact the first SS table at level 0 that contains keys from 10 to 100 with the first two SS tables at level 1. It will generate a new SS table containing keys from 10 to 150 at level 1. Today's monolithic data stores assume a server with a CPU, some amount of memory, a disk, and a network interface card. Such a server may run either on-premise or as a virtual server in the cloud. However, the monolithic data stores are not well suited for emerging data centers that disaggregate hardware into pools of resources and connect them using fast networks such as remote direct memory access, RDMA network. Nova LSM disaggregates monolithic implementation of an LSM tree to facilitate a hardware-software co-design. The idea is for the software that manages storage to run on the hardware that is optimized for data storage, and run the software that manages processing on hardware optimized for processing. Nova LSM disaggregates the software architecture of an LSM tree key-value store into an LSM tree component, a logging component, and a storage component. The LSM tree component, LTC, implements mem tables and SS tables. It identifies SS tables that should be compacted and performs compaction or offloads the compaction to the storage component. The logging component implements logging to provide high availability and durability of log records. With high availability, it replicates a log record across multiple storage components via RDMA. The storage component stores, retrieves, and manages variable-sized blocks. It manages DRAM, non-volatile memory, disk, or a hierarchy of these storage devices. Nova LSM may be extended with additional components such as a cache manager. These components communicate using fast networks such as RDMA. In essence, this architecture separates storage from processing, enabling each to scale independently. Nova LSM consists of other components such as a coordinator that manages assignment of ranges to LTCs and ensures availability of data in the presence of both component failures and network failures. The Nova LSM client is used by an application to communicate with the other components. The client component caches the assignment of ranges to LTCs, forwarding requests to the LTC with relevant data. A challenge of LSM tree-based storage system is write store. This figure shows the throughput with a 20-minute experiment. We can see that the throughput is very spiky. It drops to 0 for a short period of time between two spikes. This is because all mem tables are full, and the writes must wait for the mem tables to be flushed to disk. You can also see that after a few spikes, there is a longer duration where throughput drops to 0. This is because the writes must wait for compaction of access tables at level 0. You can also see that we must minimize the duration of write stores to improve throughput. Nova LSM may vertically scale the amount of memory assigned to an RTC, or horizontally scale the number of storage components to minimize write stores. Scaling must be done intelligently. This figure shows the throughput of an experiment with one RTC of 32 MB memory and one storage component. Its average throughput is low, only 9,000. Next, I increase the number of storage components from 1 to 10. However, as you can see, the average throughput does not improve at all. The small memory results in frequent write stores. This is because the mem table is written to one storage component, and it does not harness the bandwidth of other storage components. The paper introduces a technique that scatters an access table across many storage components to improve throughput with small memory. Then I increase the memory size assigned to the RTC from 32 MB to 4 GB with one storage component. The throughput increases by a factor of 5. This is because the RTC now writes multiple immutable memory tables to storage components concurrently. However, the throughput becomes very sparse due to the bottleneck on disk bandwidth to compact access tables. Lastly, I increase the number of storage components from 1 to 10 and use 4 GB of memory. The throughput increases by a factor of 27. This is because the RTC flashes immutable memory tables across different storage components. It also offloads compaction to the storage components. Nova LSM scales its components independently. This figure shows the throughput of a configuration consisting of 3 RTCs and 3 storage components as a function of time on the x-axis. Note that the reported throughput on the y-axis is a log scale. It varies greatly due to write stores. The figure also shows the average throughput in red inside the figure. We add one storage component every 50 minutes into the system, up to 9 storage components. After 15 minutes, we add a 4th storage component. And the increased disk bandwidth reduces in the impact of write stores. The throughput does not drop as much as before with 3 storage components, and the average throughput increases by 100,000 operations per second. After another 15 minutes, we add a 5th storage component. The impact of write stores reduces again due to the higher available disk bandwidth. We add more storage components all the way up to 9 storage components. Note that with 9 storage components, there is sufficient storage bandwidth to diminish the impact of write stores. The average throughput increases from 0.7 million operations per second with 3 storage components to more than 1.3 million operations per second with 9 storage components. The paper describes why throughput does not increase linearly. Next, I will present our enhancements to LSM tree that enable the scalability and improvement on throughput. LTC uses a preventive technique to minimize write stores. It constructs D-ranges dynamically with the objective to balance writes across them. Each D-range has one active mem table and multiple immutable mem tables. A write appends the key-value pair to the active mem table of the corresponding D-range. As you can see in this figure, LTC constructs the D-ranges according to the write load. The first D-range from key 0 to 50 contains fewer keys since there are more frequent writes to keys within this range. D-ranges provide 3 benefits. First, it compacts access tables in parallel Second, gets and scans search mem tables of corresponding D-ranges only. Third, multiple active mem tables process concurrent writes using multiple cores. In the next few slides, I will focus on how D-ranges enable parallel compaction. You may read our paper for more details on how LTC speeds up gets and scans. Without D-ranges, compacting access tables at level 1 at level 0 into level 1 is prohibitively long due to their large number, as these level 0 access tables usually span the entire key space and must be compacted together. D-ranges partition the key space and facilitate parallel compaction. This figure shows that LTC constructs 10 D-ranges. A compaction now only needs to compact 10 access tables instead of 100 access tables. Our experimental results show that D-range provides a factor of 3 to 26 improvements on throughput across different workloads. Without D-ranges, when an immutable mem table is full, we flush all its contained key-value pairs to disk. With D-ranges, LTC compacts immutable mem tables into a new mem table for D-ranges with hotkeys. This reduces the amount of writes to disk significantly because these hotkeys are never written to disk, and there will be no compaction that needs to compact them. As you can see in this figure, the immutable mem table containing key 1 are compacted into one new mem table contains only the latest value of key 1. This writes 65% less data to disk with a skewed pattern of access to data, and provides an additional 1.5x to 3x improvement on throughput. We evaluated Nova LSM with a 2 terabyte database containing 2 billion records partitioned across 10 nodes. We used the skewed pattern of access to data and 3 YCSB workloads. The read-write workload consists of 50% read and 50% write. The scan-write workload consists of 50% scan and 50% write. The write-only workload consists of 100% write. We compared Nova LSM with RocksDB and LevelDB using the same amount of hardware resources. We also tuned RocksDB knobs to achieve the best performance. This figure shows the throughput of these systems. Blue bar is LevelDB, red bar is RocksDB, yellow bar is the tuned RocksDB. Nova LSM is shown in the green bar. Nova LSM achieves 9x to 18x higher throughput because it writes less data to disk and harnesses the bandwidth of all 10 disks to minimize write stalls. RocksDB and LevelDB are based on the classical shared nothing architecture. Nova LSM shared the disk bandwidth of all 10 disks. We also compared the response time of Nova LSM with alternative systems. It reduces the average response time for writes by 11x comparing to LevelDB and 4x comparing to the tuned RocksDB. It also reduces P99 latency by 40% compared to the tuned RocksDB. There are many recent work on optimizing LSM tree to minimize write stalls. The most relevant work are separation from storage, from processing. Nova LSM is inspired by these studies. Nova LSM proposed techniques may be used by the storage layer of these prior studies. The paper presents more enhancements to LSM tree in the context of the component-based architecture. It includes scaling components independently for different workloads using lookup index and range index to fasten reads, scattering blocks of access table across disks using power of D, replicating log records via RDMA, and recovering gigabytes of mem tables under a few seconds. Please read our paper if you are interested. Nova LSM is the first step to realize the vision of Nova. Nova is a component-based SQL data store. Nova LSM is a persistent key-value store designed for write-heavy workload. Other data stores using B++ tree are suitable for read-heavy workload. With Nova, we envision an application developer will use it without sizing a server. Instead, the developer will specify the desired performance and data availability characteristics of her application, leaving it to Nova to size its components to meet these specifications. Nova will tune knobs of a component based on workload and decide which component and which implementation of a component is best suitable for the workload. Thanks, this concludes the talk.